It's constant.
Anyway, so today we're going to start another chapter 3 about the induction motor. The induction motor actually have a number of chapters, and chapter 3 will getting more important for the understanding of the induction motor. In here, we are going to looking into the equivalent circuitry. We're going to use an electronic circuit, trying to understand more about the operation for induction motor. So in here, you're going to learn more about the torque equation, how the torque relate to the speed of the motor. We also try to understand more about the formulation, how the equation look like, how we're going to use the equivalent circuitry to understand the motor operation. From there, we can understand more about the slip. I think for the homework, we've been working on the slip and also the motor speed and the power. So in here, we're trying to go through more about the equation so they understand how to work out all the homework too. So some target question we like to look into will be how we're going to estimate the motor torque, especially when the motor is starting. We've been talking about for DC motor, then we know that the DC motor starting torque will be quite large, quite high. But for the induction motor may not be as good as the DC motor. And how are we going to estimate the starting torque? So it's some interesting point we're looking into. And then another thing will be the slip. You see the definition of the slip will be, I think you all know that by now, maybe you can help me again. What's the definition for slip for the induction motor?
Slip is the difference in frequencies between rotor and stator, right? How is it? That's close.
Yeah, close enough. And mainly about the slip is the difference between the stator and the rotor. The stator we mean is the stator frequencies. And the rotor means the rotor rotational speed, right? So what about this? So that means the motor is not synchronous. So that means the rotor never can catch up with the synchronous frequency. The synchronous frequency, that means the stator frequency, divided by the pole pair. So these two can never be the same. If they're the same, we don't have any induction because the two things are rotating at the same time. We don't have any variation of the speed. So we have no induction in the rotor. Induction motor, that means we like to have the induction. So the speed between them must be different. So the slip will manipulate with this kind of operation. So later on, we will discuss more about the slip. And last week, we also mentioned about the slip. The slip will be an important element to understand how the induction look like. And then the slip also looking into the torque as well. The slip, certain amount of the slip will have a higher amount of the torque. So like for S, the slip equal to 0, what do you think? How much is the torque at S equal to 0? Matthew, what do you think?
0.
Yes, true. When S equal to 0, that means the speed for the stator and the rotor will be the same. If the same speed, we have no induction. We can't induce anything into the rotor. Nothing can be induced, that means we have no torque there. So later on, we show you some curve. You can see how they look like. But we do have something regarding the maximum. So at the S equal to 0, we have no induction, no power at all. And then somewhere when S is not equal to 0, we have maximum power, we got certain power. So that's what we're trying to understand more about it. And also rotor resistance. You see the rotor are formed by the rotor bar. We have the rotor resistance similar as the stator resistance. So later we'll examine how the rotor resistance are something related to the output power, but mechanical power from the shaft. So that's something also quite interesting, highly related to the S and rotor resistance too. So that's something we're going to examine. So by doing this one, we can't just looking into that from the motor itself. We have to use some equivalent circuitry From there, we can work out all this operation. So that's why this chapter, we're going to looking into the equivalent circuitry. So the content of this chapter, we first understand about the introduction. We're going to revisit about the sleep and the speed. That is something related to what we learned last week. We're going to give you more tutorial so that you understand what it is that will help you to work out the homework 3 too. And then we understand some region operation. So this region of operation, what's that? Some code. Anyway. No, my PC connected to my desktop phone anyway. I'm not going to answer anything. So the region of operation is not the four-quadrant operation. They are more look like the region operation related to something related to sleep and the talk. So there's another set of curves. They are really much related to the first quadrant and also second and third quadrant, but we're going to talk about it in more detail. We're going to look into three-phase system. I know you briefly understand the AC system in the EEs or Engineering 65, but you may not have gone through the three-phase system. We're going to have really brief discussion about the three-phase system because for motor, we're talking about, we're mainly working on the three-phase motor. But of course, the modeling here, the equivalent circuitry here are mainly about just motor itself. We can look at it from single phase or three-phase system. So the system we're going to present to you using so-called the per phase analysis, which is looking at each one of the phase. So because for three-phase, all the three phase are symmetrical to each other, we can only understand one phase. That should be good enough. For three-phase system, we just multiply by 3. I mean, for 3 of the phases. And then we're also looking into the modeling method and trying to understand more about the efficiency, how the efficiency look like. Can we have some formulation to understand the efficiency of motor? And then we're going to show you more tutorial. So that's how we're going to work out for this chapter. So first of all, introduction, we just showed you about the flow. So the power flow for induction motor, we now need to work out how the power flow from the stator input and then to the rotor. And then between them, there must be some power losses, including some resistive power loss like the winding, like the copper winding in the stator and rotor. That's the losses. And then the power will go through the air gap. So how the power can go through the air gap to create the power. And this air gap power, we call it PAG. That's a really popular term. So we understand how the power flows. So all the power from the stator, then we go through the air gap to the rotor side. And then to understand more of the power, the only thing we can do, I think the most popular way we can do is model the whole induction motor by using some circuitry. So one of the equivalent circuitry we have been used by all the scientists will be shown you here. Then from there you can understand how the operation look like, how a circuitry can relate to the operation. It seems that in many scientific research or study, we tend to use some equivalent circuitry to do that. The equivalent circuitry may not 100% represent the whole operation, but it's a simplified way we can understand how we model, how we examine the operation. So from there, we can able to work out the efficiency and the power losses. So one thing will be the air gap power, which basically will be total power transfer from the stator side to the rotor side. So when you go to the rotor side, it becomes our mechanical output power. So this air gap power is something we have been using in this chapter to show you how the power connected between the rotor and the stator. So it's just more look like we try to link them between the electrical energy to the mechanical power output. Then you can see that we also have the rotating magnetic field. So the rotating magnetic field actually is what we're trying to cutting the system. So we got stator and then we got rotor between them with the air gap. Right? So the stator actually will be cutting. So the power will therefore transfer through from the stator to rotor. And then it will therefore cutting the rotating field. I think between them, we got all the field. These are the rotating field that will be cutting through the both of them. So that means this kind of the rotating field will cutting through from the stator to rotor. And we can also see that this air gap power is something related to the power passed through the electromagnetic power to the air gap size. So later on, we will show you more detail about how they look like the air gap power. So this chart will show you how the operation look like. So firstly, of course, we do have the electrical power, which you can see that from the input, we got the input voltage, V1, input current, and then we do have some power factor related to them. And then here, three-phase system, we're putting the 3 in here, three-phase, so that's the input power. You can see from the electrical input side. And so, of course, when you pass through the stator winding, we do have losses. That will be related to the how much resistive losses. So, of course, if we want to get the 3-phase, then we can put the 3 here to replace the 3 of the losses. But if we want to go for the per phase analysis, we don't need to worry too much about it. And the power will have the air gap power will go through the air gap. And then once it go to the rotor size, then we do have the copper losses in the rotor, like the rotor bar. And then the rest of them will therefore become the mechanical power. So that's the power we need to understand more about it. So mechanical power is supposed to come out from the rotor shaft, and then after the reduction or deduction from the friction or windage loss, that was the real output to drive the output. So basically, then you can see power flow will be as such. So let's firstly, before we go any further, let's go to a few tutorial example to show you how the correlation between the slip and the speed. So this kind of example just show you how we use the basic equation we've been talking about for the last few chapters. And then some of them are highly related to your homework 3, so that we just go through them. This you can see that when we go to this tutorial, they're pretty much quite straightforward. We only need to use a few equations, mainly about the synchronous speed equation and also slip equation, and then that's all. So that's why I can see that they are quite simple and straightforward. I think some of you may have already done the homework 3, then you can compare with this presentation. So firstly, we say we got a 4-pole 50 Hz induction motor, have a low load speed. No load, that means we do not connect anything, just more look like open circuit test. Sometimes we call it open circuit test. That means we are not connect to anything. So that's really similar to transformer open circuit test when we're not connecting anything in the output side. So when a motor just rotated by itself without connection, then that means the output current could be quite small. Because we all know that the output torque, really much, no matter what kind of motor it is, still proportional to the motor current, to the output current. So that means when the low load test, that means output current or motor current can become negligible. Then we see that at that time, the speed is running at 1492 RPM. And also full load because we use a mechanical load to load the motor, so the speed is supposed to be lower. Then we calculate synchronous speed, the no load slip and full load slip, and also speed regulation. This is typical calculation to understand more about the motor. So in here, we use typical, that's a basic equation. I think we have been using it. The synchronous speed will be equal to 120 F1 over P. So where the 120 come from? Anybody can tell me? Why we're 120? I think you used that equation in the past, right? Where why we're 120, F1 is the input frequency, like the electrical frequency. But electrical frequency and the mechanical speed are different by the pole pair, right? So that means anybody can give me a hand how that equation comes from? Anyone? How about this gentleman?
I'm not sure.
Anyone can give me a hand. Suddenly forgotten how to divide it. Please do give me a hand. How about you have me?
So I remember seeing the equation a while back, but without the
Almost, yeah. Just a little bit. I mean, you compare the unit, the hertz, the frequency. F1 is the input frequency are related to the hertz. Hertz is per second. And then we try to change them into speed. Speed usually will be RPM per minute. So can you think about any
Oh,
calculations?
60
with that?
squared, it's just from seconds to minutes.
Yes, from second to minute, right?
I see.
So that means the formulation will be F1 is in terms of the hertz, and then we multiply by 60 become per minute, and then divide by the pole pair, right? Pole pair. So that means that's why it becomes this, right? That's how it come from. So we use this formulation quite a lot to try to correlate the electrical frequency to the mechanical frequency or mechanical speed, right? They are not the same. If only pole pair equal to two poles, they are equal to each other. But when we have high number of pole pair, then the speed getting lower and lower. So you can see that last week we do have a table to you to show you when we have two pole, they're the same, and 3,600, and then four pole, 1,800, and six pole, we got divided by 3, and so on. So that's the same. We are using this formulation to do that. So now then, the slip, that means it's more look like a percentage or ratio, how much the rotational speed are different from the synchronous. So that means we have the synchronous here, and then minus the speed we have here, the speed here, and then compare with the base. So that means we got 0.53%. So this is a no load. So that means the speed supposed to be really high speed, really much close to the synchronous. They cannot equal to synchronous. Once equal, they have low induction, low power at all. But even though no load, we still need to overcome some type of the friction or losses. So that means this is the power we have here. And then we can also compare the full load here. Full load will be this one, 144 here. And then the comparative speed, just the subtraction, these two minus this one, the difference between the two speeds is the slip. And then divide by the base, then it will give you the in percentage. Okay, so that's 2% we can get. So full load, so all the slip usually just a few percent. You can see from here, and without any load, that means without any connection in the mechanical shaft, the speed would be really much close to 0, but cannot be 0. When 0 and low induction, really small percent, maybe 1%, 0.7%. And then in full load, usually a few percent depend on the motor's design. 5%, 4%, 6% will be some typical counterable. And then the speed regulation is just to see this is the range of the speed operation. So any motor under that domain, the speed will only vary between these two, only vary between 1492 to 1440. That's the range because there's a full load, that is a light load. So this the difference between these two, we call the speed regulation. So that's how we get to regulation 3.6%. So usually for motor, we don't want any too much variation between the full load and light load. So that means if the motor fluctuating the speed too much by different load connection, that's not a good way for the motor. Of course, in terms of the motor control, we can use power electronic to control the voltage, can control the frequency to regulate the speed here. So we can have a more narrow changes of the speed. So that's how we're trying to look into. So this example just shows you how we understand more about the speed regulation. You see the formulation and all the equations are quite standard, quite straightforward. Any question up to this point? Okay. Yes?
So the speed regulation is like a speed range.
Yeah, more look like speed range. Speed regulation, that means you see when any system, no matter is say a battery or any output source, for instance in here, so this suppose 120 volt, but when you put more load there, when you put say hair dryer, you have more current driven, may not be 120, maybe 118, right? When you don't connect to anything, the voltage may not be 120, maybe 122, right? So the range of the voltage from this power point could be from 122 to 118, right? That's the voltage regulation. Of course, for good system, we don't want too wide voltage changes. So the regulation percentage, we tend to be as small as possible to become a good system. So for motor as well, so the range speed regulation is changes from this speed to that speed. You like to be small. But if you cannot do that, then we can use power electronics to control the speed to a constant speed. So that's what we're trying to do. So next, then example to show you is the frequency change. So how we see the frequency change effect. So the example is if an 8-pole induction motor run at 3% slip on 50 Hertz. So of course, all the motor have certain slip, you can't. And then if the frequency now increase to 60, while the same slip is maintained. So we're going to calculate the original synchronous speed, original motor speed, and new synchronous speed, and new motor and percentage of speed increased. You see a motor, usually they program or design a certain slip as a maximum performance or the best performance defined by the slip. So usually say, oh, 3% slip is the one of the best performance. Even though we change from 50 to 60, the best performance slip will usually unchanged. So that's one of the design criteria or design popularity we tend to use. So let's see that. So the synchronous speed, rotation speed synchronous, again, we use this formulation. Now we put the 50 into here, and then divide by the number of pole, 8 here, say 750. Very simple, straightforward. So we don't need to just purely adapt the equation without any complication. You can see that all the calculators here are quite straightforward, simple. So that means the induction machine sounds really complicated, but actually the way I present are very straightforward, simple. You just remember a few equations and then that's all. So like this equation, we have been using it quite often, even though for the homework 3 too, yeah. And then for the mechanical rotation speed, right, will be ns minus 1 over s. So this, you can see that this is mainly the difference between the synchronous speed from the motor speed, right? So that means that is 727.5 RPM. The slip here is how much is different from the synchronous. So now then the mechanical motor are dropped by 3%. So with 1 minus 3% will give you the actual speed of the mechanical motor rotation. So that will give you say 727. So you can see that these two are different by 3%. So it's quite straightforward. So you can, so this equation is just very straightforward. You don't really even need to memorize, you just come out from the understanding how the difference between the two motor speed. So now then we change to 60. So we use the same equation and then change to 60. Of course, the speed will go to 900 RPM. Again, we can use the same kind of slip and we calculate it. Now the speed will go to 873. Just so these two and these two are the same, using the same set of the equation, but now we're changing the speed between 50 Hertz to 60 Hertz. So usually our frequency will be in this country, United States will be 60 Hertz, in UK will be 50 Hertz. So depending on which location we tend to use. So 50 and 60 are common speed for the power source. And that the speed will be increased. So you can see that if we change from 50 to 60, that can be easily done by using an inverter. Now, if you have been using inverter in the past, like last year, we have been working on the inverter study for solar power, then you see that you can drive the motor or drive any pump system, rotation system by using any frequencies. So for instance, you say you can change from 50 Hertz to 60 Hertz, then you can see that the speed will be increased by this percentage. That's that. So you can see that the formulation here are quite simple and straightforward. So key thing, you can see that our induction motor can be driven by the power source frequency. That frequency can be anything. If we, of course, in here, we use 60 Hertz with 60, but if you're using an inverter to drive it, the frequency of 50, 40, whatever you like. So that's so-called variable speed control. So variable speed drive, variable. Right. So this term VSD, if you go to any internet or textbook, you can see VSD is a really famous term, which is trying to say, and we can use an inverter to control the motor speed called VSD. All the inverter or motor controllers should have this capability. We can change all this frequency to any frequency we drive so that we can have a variable synchronous speed, right? All right, any question? So all these tutorials are really similar to your homework 3. So if you haven't done the homework 3, after you've seen all these tutorials, you can find the homework 3 very simple and straightforward. So we also examining the breakdown, right? Breakdown is the term we say is not really called breakdown, is a terminology we call the motor has a maximum power or maximum torque performance. You see the torque for the induction motor are changing. It's not a horizontal straight line, but it varies with the speed when we have constant voltage input to the system. So that although you can also see we got the constant torque control and constant power control, that's another manipulation. But here for any given motor, if you don't control the torque and anything, let the torque to vary with the speed, then you find that the motor has certain speed, which the torque level will be maximum. Everything will be like that. All the curve, all the system might have some maximum capability at certain speed. So like a electric vehicle or maybe automotive, gasoline car, certain speed, the gasoline part ICE have a maximum torque. So similar to motor, everything. So we got certain slip here, we call it SM, or sometimes they use S breakdown. That's at the steps time of the slip have a maximum possible torque. And then we, in our jargon, in WD jargon, we call it breakdown torque, or something like the pull-out torque. So this kind of breakdown torque have some region we need to be quite interested to look into, which at the breakdown slip, the motor with absolute maximum capability. So all the motor at that particular breakdown frequency or breakdown slip, the power will be, not the power, the torque will be maximum. So usually the power will also become maximum really close to here. In the next few pages, then you can see some characteristic, how the torque change with the speed. Then you can see how the overall picture. Here, I just show you the terminology first. Next few slides will show you how the curve look like. And then, however, you see that beyond the slip, when we operate beyond the slip, that means on the left-hand side of the slip, or a so-called the larger slip, then we have so-called the no return. No return, that means if you operate the motor at the maximum slip or maximum torque parameter, when the torque or on the speed is slightly less than that, then you enter into a region that's not a favorable operation. So that means if we further manipulate with the torque and the speed, the motor become unstable, highly unstable. Can very easily can become stalled, the motor completely stalled. So that's the region we don't quite like to operate. And then another region when the speed is higher than the breakdown speed, then this region will be more favorable. We call the low mode slip operation. So that is to say we got this is the maximum value. So we got the speed here. So that slip when this region, then that will be favorable in this region. It's unfavorable. Once we enter in this region, the motor very easy to get stalled. So later on, we will see how the curve look like. So that means in here, I introduce you to a term that means called the breakdown slip. That breakdown slip will divide the motor operation into two halves. One half on the right hand side will be really favorable operation. The other half will be unfavorable, can make the motor to stall or not able to control properly. Under variable torque operation, variable load operation. So later on, we can see how they look like that. So later on, we'll show you the parameter, how the breakdown and what maximum torque will look like, how the breakdown slip shall look like. So let's see tutorial first. So 6-pole 60-hertz induction motor develop maximum torque at 900 RPM. We are going to calculate synchronous speed and the slip at the maximum torque and more slip at the full load if the full load slip is only 40% of the breakdown slip. So again, we can calculate synchronous by using the same formulation. So now we have 60 here, and then we also have 6 pole in here, that become 1,200 RPM. So now you can 100% remember, if you have 60 Hertz operation, 6 pole, that means you divide by 3, right? 1,200 RPM. And then the sleep at the maximum torque here. Your maximum torque is 900 RPM. We just put 900 in here, put 120 here, then we can get 25%. So maximum torque appear to sleep at the 25%. And next is calculate the speed at the full load if the full load speed is only 40% of the breakdown sleep. So because we say so we have now 40% here, and then multiply by this 25%. So the full load sleep actually will be 10%. So that means if you see the operation here, you got a curve here. So this could be about 25%. And then one of the good operations here will be we got 10%. Here will be the maximum torque. So that's a full load. And here will be the maximum torque. As I said, the maximum torque doesn't mean it's the full load. The maximum torque is the maximum capability of torque can produced by the motor. But the full load, that means is the power could be the full load. So that means the power and the speed need to be the torque and speed multiplied together give you the full power. So that is to say the maximum torque is the maximum possible torque can produced by the motor. But the normal operation, most operation, we don't need to operate on that point because beyond that point will be more stable. This region is more stable. This region is unstable. So that means we have to look into how to operate the motor in this region. Later on, you can see the curve of the region of operation. So, and then you can see that the maximum torque here and the full load operation will tend to be also on that region too. And then the full load speed is only 10% in here. So that means the full load rotational speed, we have synchronous speed and multiply 1 minus 0.1. So that means, so this is same with this one. So that means the full load speed will be 1080 RPM. So again, this kind of calculation will be quite straightforward.
Does the 0.4 multiply to the supermax torque is just the what we were talking about on the previous slide, where it's like you want your tolerance to be under 50%?
You see,
I'm trying to figure out where the 0.4 comes from.
Yeah, 40% is the information provided by the question. The question is that at 40%, we got the full load situation. As I mentioned, all the motors, we have the maximum torque, which is so-called the breakdown speed. And then, but the maximum power operation may not equal to that because all the motor tend to operate on the right side of the maximum torque region. That's the region being able to vary the speed and vary the torque more comfortably without any chance to stall the motor. So when we go through this field tutorial, we just showed you some terminology. We haven't go through the characteristic first. So in here you can understand how we work with the sleep, the breakdown sleep, and also the synchronous speed. So we just go through this field formulation. And then this tutorial will show you some specific operation. Conveyor system, which require motor running at 700 RPM. And then the power source is 60 Hertz and select the pole pair and calculate the exact speed at 4% slip. So when we select motor, when we give them with certain power source, like our power source here will be 60 Hertz, we can select motor will be either 10 pole, 8 pole, and 12 pole. So in here, we know that the pole pair will affect the synchronous speed. And the synchronous speed will also really much close to the motor operation. So that means he can see that a motor, we know 4% slip will be how much 4% deviate from the synchronous. So this field operation, we can see what's the best motor we can able to achieve close to 700 RPM. So to do this one, we can, each case, we can use the F1 to calculate synchronous speed. So 120 times 60 divided by 10 poles, we got 720. So 720, if we, after deduction from the slip, we got 691. That's RPM we have. And then another motor have 8 poles. Again, we use the same formulation. Multiply 60 divided by 8, we got 900. So after deduction for the slip, the normal operation will be 864. But we want the motor running at 700 RPM. So that means 800 something will be too fast for our conveyor. And then another case will be 12 poles. Again, we put 12 in here, we got 600 RPM. After deduction for the slip, which only about 500 something. So you can see that that will be too slow. So for all three comparisons, we found that we should choose a motor 10 poles, which more close to 700 RPM. This is also a very simple tutorial. Show us how we select motor by using number of poles. In the next tutorial, we try to go through the efficiency of a motor. So the losses for the motor, we do have some mechanical power losses. We got air gap power. And especially the question is say 4-pole motor 50 Hertz, 225 kilowatt from the input and deliver 1450 RPM. The copper losses in the rotor will be 800 watt. So we have to calculate all 5 of them: synchronous speed, the slip, and air gap power, mechanical power output, and efficiency. So again, the synchronous speed will be 120 multiplied by 50. Multiplied by 50, and 4 divided by 4 pole, we got 1,500 RPM. So the A part will be straightforward. And then the slip. So because you say deliver 1450 here, then the synchronous speed will be 1500. So we can get the slip will be equal to 3.33%. So now then is air gap power. We haven't quite show you this formulation first. But there's a correlation between the copper loss in the rotor related to air gap power. So you see air gap power, only when the air gap power passes through air gap, only a portion of power will dissipate to the copper in the rotor. So that will be a ratio of S, because S is quite an important parameter. That's why we always talk about S. So do remember this formulation. Later on, we'll go through how the formulas come from when we go through the equipment circuitry. But these are famous formula. You can start to look into that. So that means we can therefore look into, we got 800 watt in here and divide by the slip. Then we can get the air gap power will be 24 kilowatt. 24 kilowatt here. And then we can see the mechanical power. Then the air gap power is 24,000. And then we can subtract from here. Then we can get the mechanical power, 23.2 kilowatt. So the efficiency, the power join 25 here. So that means that is the input side. And then the output will be this one. So the overall efficiency will be 92.8. So you can see that the formula, we are using a few formula here. We can able to compute a lot of the parameter for the induction motor. So major formula you can see here, you can see in here, the synchronous speed, the slip, and also air gap power, and that's all. And mechanical power will be this. You see this formula, the air gap power. The mechanical output will 1 minus S, and then the electrical, the rest of that S portion go to the copper loss. The remaining will all go to mechanical power. So that's why I can see that air gap are divided into 2 portions. So copper loss and also mechanical power. So that's why I can see that in the first chart I showed you in here, the air gap power divide the copper loss and also mechanical power. So S base in here, 1 minus S go to here. So that's quite something quite special. So how do we get that? In the equivalent circuitry, we're able to show you what it is. But here, we just give you some MP information, how they come from. So next, we're also looking into the starting condition. You see a motor starting, the torque also quite special. So for this example, we got 6-pole, 60 Hz induction motor have a rated speed of 1140 RPM. And then we're going to calculate the synchronous speed again, yeah, and the full load slip and starting current frequency at a standstill, and then the speed when the rotor is 12 Hz. So first of all, we have 6-pole here, 60 Hz. So again, we got 60 here and 6-pole calculate, we got 1200 RPM. And then the full load speed, the full load, that means usually we also refer to the rated mean the full load condition. So we got 1440 in here. Then we got synchronous in here. Then we get the full load slip will be 5%. Starting means the motor just start, the motor is not rotating yet. So when we just start the motor, so that's why starting also refer to the standstill. When you see the starting or standstill, then that means the motor is not rotating. So in this case, not rotating the slip, the difference between the synchronous and the motor, of course, the motor becomes 0, then that means they will become the synchronous. So all the speed will go to the, so that means the synchronous, the frequency in the rotor, or the starting frequency in the rotor will therefore equal to 60 Hz. Just like you can see that when the motor is stationary, so the induction motor just like a transformer. So all the input frequency, 60 Hz, will all transform or pass through the air gap to the rotor. So the rotor will therefore experience 60 Hz. So the frequency of the rotor then will become 60 Hz. Yeah, as simple as this. So we got some terminology. We use FR here, but sometimes we also use F2 because F1 means the stator, F2 means the rotor, or F1 or 1 mean the primary, I think, mean it, or mean the stator, and 2 we mean secondary, or mean the rotor. So that means we got 2 kinds of the system, but we tend to write down both of them so that you can easier to understand. So next question D is calculate the speed when the rotor frequency is 12 Hz. So at 12 Hz, then we calculate how much the slip is, refer to the base 60, then we got 0.2 here. And the rotor speed will be, we use 0.2, then we can therefore get 90 RPM. So that is how we able to get the speed at rotor frequencies 12 Hz. Okay, so that's a quite straightforward calculation. Try to make use of the synchronous and motor. You can see that there only have a few equations, but you do have a clear mind between the number of poles, the synchronous. Synchronous will be reduce the frequency by the pole pair. So that means, so when you talk about the RPM, we usually will refer to the synchronous speed. Yeah, the synchronous speed will be used for this. When you talk about frequency, electrical frequency, the motor electrical frequency, the motor frequency is directly coupled for the input frequency for the air gap. So we cannot change the frequency. We can only change the RPM for the mechanical pole pair, but we cannot change the electrical frequency from the stator to rotor. So that's one of the key things you need to separate them. And then next tutorial, we're looking into the multiple speed operation calculation. Let's see what it is. So we now again have a 4-pole machine, 50 Hz induction motor, operate at 3 possible load. So at light load, of course, the speed will be higher speed. So medium speed, and then there will be lower speed. When we heavy load, of course, the speed we were loading, then the speed will be lower. Then for each case, we are going to calculate the slip and the slip speed and also rotor frequency. So again, for all 3 cases, they all refer to the same synchronous speed. So that means, again, we got 50 Hz in here and divide by the pole pair 4. Then we got 1,500 RPM. So we use the 1,500 RPM as a synchronous speed for the calculation of A, B, and C. So then for the light load, we got 1,470. That speed. And medium, we got 1,440. And the heavy load, we got 1,4110. Then we got 3 cases here. For each of the case, we can calculate the slip. Slip will be usually expressed them in a percentage or a ratio. So that means will be 1,500 is a synchronous, minus 1,470 divided by this one, you got 0.02. And then so on, we can get the rest of them. They're straightforward from the formulation. So obviously, you can see that the heavy load, we usually have the slip will be slightly larger. The light load usually will be small. Small, that means they are more close to the 0. And then the slip speed is the difference between the synchronous and the speed of rotation. So that means there's a 30, 60, and 90. So that is the slip is the difference between the slip from the maximum possible slip for the motor. The maximum possible slip for the motor in here will be our synchronous, 1,500. When we have more load connect to our motor, then it's more deviate from the synchronous. The best, the high speed we can have the motor. So that means for we have heavy load, we only have 6, we only have 90, much more different from the synchronous. And then the rotor frequency, as the frequency, we are using the input frequency from the electrical side. As I mentioned before, it's only a transformer. You cannot change the frequency. You only can change the rotational speed. So that means we use the slip here to calculate the rotor frequency. So that's the frequency appear when we using an oscilloscope. If we can to measure the current inside the rotor, that's the frequency you can see from there. Of course, we cannot measure because closer picture, but if you like to measure, you can still able to do it, but it's rotating. I don't think you can measure, but this is how we calculate that. So that to say the rotor frequency, the rotor current frequency will be quite a low frequency, only a few hertz here. When we have more heavy load, the frequency will be higher, and the light load, the frequency will be 1. If load disappear or low power generate, then you can see that the frequency will close to 0. Those are how the characteristic for the thing look like. So you can see that my remark here will be the slip speed is the actual speed in RPM between the rotating magnetic field. Rotating magnetic field is the synchronous speed. As I mentioned, the rotating field, every period you go to one pole pair and next pole pair and next pole pair. So that's why the synchronous speed or the rotating magnetic field will be equal to the input frequency from the stator divided by the pole pair. So that is the speed difference between the actual rotation for the rotor. So that's so-called the slip. So that's why the slip is the difference between these two. So I'm not quite sure after we've gone through 3 chapters, do you have a good understanding between the synchronous and the rotor speed and air gap field? There's a few new jargon in here, right? So do try to understand it. If you're not quite sure, then we can discuss again. I'll go through my notes. But this kind of concept would be a really popular concept for all the induction motor. Induction motor is really famous topic for all the electrical engineers. So on the internet, there's a huge number of the material you can go for. So I don't think you have any difficulty. You can go for my notes or my YouTube channel. You can, I'm not quite sure, you visit my YouTube channel. I record all my lectures in my YouTube. I also have the link. You can review them. And then you can also visit many other professors' channel. So anyway. So the key point I'd like to take away will be, so our sleep speed here, we mentioned, when we say speed, so that means more look like the mechanical speed, not the frequency, not the electrical frequency. So that will be more in RPM. And then it just show how much the voltage lagging behind the rotating field. The rotating field always rotating in some way proportional to the input electrical signal, but just divided by the pole pair. And then the rotating keep rotating with this pole pair, next pole pair, next pole pair, and so on. And the rotor try to catch up. But they're always with some lagging due to the loading for the rotor. When we put more heavier load in the rotor, then it just lagging a little bit more. So that's why I can see that in here, when we heavy load, then it just the difference become more lagging further in RPM. And once we do that, then we go slightly higher in the rotor frequency. So we can also see that the load actually affects the motor thing. In theory, have we increased the load, then we can reduce slightly of the motor speed. That will same for everything. Even though our battery as well, we connect more load, more heavy load, the battery voltage will drop slightly, right? If we release the load, the battery voltage will become higher. Even though for this power point as well, the voltage also vary with our loading connection. So that means for motor as well, when we connect more load, when the load increase, that means more heavy load, more torque increase required from the motor, then the motor slow down, the speed will slightly lower. And when the motor slow down a little bit more, then the sleep will be increased. The sleep, that means the difference will also increase. So, and that means when that increase, then the relative motion between the rotating field and the rotor will therefore increase. So that is a kind of the feedback, internal feedback control, because we do need a difference between the rotor and the field. If there's no difference, we don't have any induction. We do need that difference to create the induction. That's a principle for the induction motor. If they exactly equal, we have no induction, because all the induction are related to dphi dt, right? All the voltage are related to n dphi dt from the Faraday's law. So the relative motion means this kind of the variation. Without variation, without changes, we have no induction. So that's the principle for induction motor. That's how our induction motor comes from. So we've gone through a few weeks. So try to make sure you understand the basic principle for induction motor. So the slip we are usually can be represented in a ratio as relate to the synchronous. And then for the rotation slip, then it is S multiplied by the synchronous speed. Yeah. So that's a two terminology we usually try to refer to. So after you've gone through 8 tutorial, you should now have a really good understanding how to work out all the sleep, everything. You should have a high confidence to do the homework free, I guess. If any problem, office hour, Wednesday, come to see me. So we just showed you some typical parameter because we've been mentioned so much about various sleep, ratio, frequency. Let's see some typical motor example. Then you can see what kind of the sleep we're talking about. When we see a few percent, what kind is a few percent? So for small motor mean less than 10 horsepower, small one, So usually the typical slip will be between that kind of the range. And then for medium motor, with this one, the large motor, then the slip will be this kind of the range. Then of course, if a motor, we try to run them at very heavy load. So that's a light load slip. Light load, that means we not connect to anything. We don't connect to heavy load, just let the shaft to rotate by itself. Then usually the slip will be quite small. So how small is small? Usually that is the range we are talking about here. And then when we run the motor with some heavy load or peak load or maximum load, then of course the slip will increase to just 5 to 6% like here. Heavy load could increase to 6%. That's quite common. We seldom increase to more than 10% or 20%. This is quite rare to see that. So 6% would be quite typical. So for our 1,500 RPM motor, then 90 RPM will be quite a typical difference. So that means typical light load speed just vary between 0.5 to 2%, but that range can be very amount here. Yeah. Not all the motors are exactly the same, but here just give you some typical parameter, how the slip look like for various type of the motor. So now it's a really beautiful curve that's so important. We have done all the description for the slip and the speed. Let's see how the curve look like for actual motor. So the vertical line is the torque, and the horizontal line is related to the speed. The speed have a two kind of the region we like to look into. They both represent the speed and the slip. You see the speed and the slip are similar thing, but they just reverse a little bit. So for instance, in here, when we start the motor, the speed equal to 0, right? And then when we start to accelerate the motor, the speed will pick up and we go to somewhere. And that is the breakdown position we mentioned before. SM is breakdown or the maximum torque. So that's a breakdown region in here. And then after if further you increase, then you go for region. Then when the S equal to 0, that means the synchronous speed and rotor speed will equal to each other. We have no induction. So that means this region will have no induction. So we're not inducing anything in the rotor. The rotor will lose all its capability, all the power. And then beyond this region will become power regeneration. So we call it stable operation. We tend to operate the motor in this region. That's a good location to work with. Why anybody can tell me why this region will become more favorable after we discuss for quite some time? Can you from here, we can say that this is more favorable? Why this region will be more favorable? I have a quick thing about it for 1 minute. Yes?
Because there's less lagging speed.
Yes.
Lagging speed.
Lagging speed? No, not only that. That's more look like how to say that means when we put in some additional force or torque to the motor, load to the motor speed will therefore decrease, right? But when we release the torque, the motor speed will recover back to origin. So that's how we think about how the system become more realistic, a stable system. Because we are able to control when we the more low the voltage or the speed will drop much faster. The system can recover by itself naturally. Just like battery, when you put more load to the battery, the voltage will drop. But if you release the resistance, the voltage back to original. But if you put in more resistance, you drop the voltage, and then when you release the resistance, the voltage continue to drop. That is inconceivable. Your battery is not stable, right? That's how we call stable or unstable. When you power from here 120, when you put more low hair dryer, it drops slightly. But when you release the hair dryer, the voltage still continue to drop, cannot recover. That will be disaster. Here will call you, right? So similar to here, you think that would be more favorable region for that kind of operation? That's how we say the system can cover or not. How we mention about stable or not. So this line means the speed. Zero speed increase to the maximum speed, and further increase the speed means what you try to feedback energy back to the households, right? We don't consider this at the moment. Just think about that region. What do you think about region? Obviously, you can see from this region. That's the maximum torque. When you further increase, this further increasing the speed at this point of the speed, right? If you increase the torque, increasing the speed will move this way, and that's why you can reduce the speed. And then when we cover the torque, reduce the torque back to here, the speed will increase. So this curve will show more stable, more reasonable curve. So that means for a certain speed, certain torque, when you increase the torque, the speed will decrease, and vice versa. So the system can be covered by itself. So that means we call it stable. So the curvature will be in this kind of slope. You get that?
Yeah. We go with the unstable. Yeah. So what happens?
Then next, that's the question I'm going to answer next. So if you understand this region, how we become stable, that means the system can able to recover by itself by using when changing the torque and speed, the system can go back to original state. That's called the state. Like the battery, when we increase the load, we go back to original voltage. That's what we like a system. And naturally, a system should look like, you call it more stable system, rather than go through something like low return. So now that you've understood the operation, then let's think about this curve. Why we say it's unstable? Give you 1 minute to think about that. That's the characteristic for all the induction motor. How many? Yeah. I think you get the answer. So can you tell the class, what do you think about that? Why is unstable? Please give me a hand. I just forgot how to explain it. So you show me how we can say this region is unstable, please.
I was talking to Matthew and we were saying that the torque and the speed are both increasing, and that doesn't seem right, and that causes the current to increase. And for induction motors, is voltage proportional to speed as well, or is that just with DC motors?
Only for this motor.
Okay.
The speed more complicated in induction motor. It's something like that, but we don't say that. Yeah, okay. Any other comment or any other suggestion how we can able to experience with this part of the curve is say unstable? Let's look at this case. If we're operating at that point, we have this kind of the low torque. So what we're thinking will be, now we got this low torque, and then when we take away the load, expecting less loading to the motor should increase the speed. But that's not the case. When we reduce the low torque, we jump to that point, the speed will reduce the load. Less loading, the speed will also decrease. And then we further reduce the load, the speed will further decrease, eventually go to zero speed stop. So you can see that for any loading system, when we take away the loading, the system should be more happy, can able to run faster, but not the case. We need that reverse until the system completely stop in here. You continuously remove the load. That's the issue we don't like that. So that's why I call it low return. You see my notes, I say no return somewhere. Somewhere I don't remember where that. breakdown torque, point of no return. So beyond that, so that's why when we control the motor, you see the motor curve is so large range. So we can mostly control. We have this whole range to control. We first start the motor, then go through the maximum torque, is able to drive anything, and then we try to operate the motor in this region. You just stick control and then try to operate on that region. Because it's more naturally, you can control motor by correlating the torque and the speed. But in fact, unsafe region, anything happen, then the system will stop.
How long does it take to go from the unstable region to the stable region from sense?
That's a good point. Yeah. When we start the motor, of course, all the motors start from here, and then we start adding the motor getting high voltage, and so on. Motor will accelerate. And then so that means accelerate torque will be quite special. You don't try to reduce and increase the torque at that point. Otherwise, the unstable region will continue. So that means you need to make sure when we start the motor in zero, we quickly pass through that region, go to that region. That will be stable. Once pass through the maximum torque, the motor will become stable. That's why many operations, the motor drive system, you can't start the motor. When you start it, then you become stalled because you are not control motor to move on from that region, quickly go to this region. That's the important point. All the motor tend to operate in this region. Because in this region, you can also control because of power in motoring and regeneration. This is called regeneration. You're going to spend some time for power regeneration. For all the motor, including mobile, electric vehicle, even the industrial drive, we also need full operation. Okay. For electric vehicle, of course, when you drive the motor, you do brake, then the speed will change in such a way that you can return energy back to the consoles. So this the regions we tend to operate most often. But if only for motor, that's the region we try to operate. Okay, any question? So the curve also quite special. You can see that in here, we tend to use the speed. So the speed will be like that. So more, we're quite familiar with the torque and speed curve. The torque in this vertical axis, the speed in this vertical axis. But however, the modern people, they try to use the slip, as we mentioned before. So now that we got another label curve, that slip equal to 1. I think we know that, yeah. And then that slip equal to 0, and so on. That slip equal to negative. So you can use our equation. When we do the equation, you can convert the slip into S. So when you look at the torque speed curve, they can both represent in the horizontal axis, can be speed or slip. They are both the same. Why we need to use the slip to represent it? Because firstly, S equals 0, that means no induction. We have no induction at here. So that means we have no induction. That means the torque equals no energy in the rotor. And then we usually prefer the slip to be small. So that's the reason where we are able to have the induction. Of course, the whole thing has the induction anyway. But this region, from the characteristic, later on from the current circuitry, you're able to go out on the power level. This region, from maximum power to 0 power. That's the normal operation region we have for the motor. So this region is called the breakdown. We usually mean braking zone or this kind of braking or the parking. So I think we also work in this motor, we also talk about the parking mode. When we want to reverse the motor direction, then we can use another way to record the parking. Reverse the polarity for the motor. So this one, the region, you can able to force the motor under the parking operation. It's a kind of the braking, but this braking is not using a resistor to brake the motor, but using reverse voltage to brake it. So this region, we will talk about that. But most of the region we tend to discuss will be in here, or we focus on here. And then, of course, this is the region So you can see that that is the quadrant one. So this is the power regeneration, and quadrant 2 for the power regeneration. So basically, that's the region of operation we try to operate. So the first is unstable region. We just mentioned about that. Why is unstable region? Because that is the torque and speed operation. It's not coordinated really well. If you go to this region, although with the motor starting, we try to pass through that as soon as possible, as quick as possible. So that's one of the control method we try to work on for the induction motor. But that may happen when we do have a heavy load in the system. When the load is too heavy, when you want to start the motor, then the operation may tend to go to the unstable region quite often. Or sometimes when the voltage dip, when the input voltage may be dropped from unnecessary voltage drop due to the whole power distribution system not unstable, then we may also end up with this unstable region. So once you do that, then the stall will happen, will go to that point. So that's why this we also call the point of low return, because this region, the torque is inversely proportional to the slip. That's the thing we don't quite like. Yeah. So once the slip exceeds this one, cannot deliver its own. So this is the S, right? S greater than SM. Yeah, so that's the point. So if that's the case, we need to think another method to do that. Let's think about if the motor really go into this region, when the motor going to stall, what can you rescue the motor? How are you going to do that? Think about that. So that's a part of the motor control. We tend to control the motor in this issue, but once start the motor, you cannot start. Already you cannot start. What is the issue? The issue will be here. Then you need to think about how you work that. So one thing will be, firstly, reduce your mechanical load, let the motor to start running, go into this normal operation first. So don't inject too much load. If too heavy load, you have problem to start motor too, right? So that may reduce some mechanical load, and then you may need to restart motor. Anyway, so I'd like to show you this curve. It's really, really important curve for induction motor. All the textbook, all the literature, all the internet will talk about this curve. So do spend some time to understand this curve. Maybe you tonight you go to the internet to see what is that curve like that. Really, so important. All right. See you again on Wednesday. So do finish the midterm. You got one more day to finish it. The midterm is really much simple, really similar to previous one. So should be okay. See you then.